Right. So if you remember, we talked about this relationship, right? Why is D lambda named closer? I like that. Only way to come down here, I want to do it. Right. Right. So anybody remember these little relationships here? Besides this, right? If I have think much of my mouth. Right. So what's here? Let's say we have something like this, right? Just now I'll go into the proof, right? The objective is to prove this and be able to apply it, right? Let's say we have something like this. Let's say we have our two slips and we have our screen, right? Remember, rays will come out of this slit and this slit, right? And they will undergo interference. If they undergo constructive interference, what does that mean? Right? And if they undergo destructive interferences, nice. There is something you need to remember and to know as well, right? Everything I give you here in the handout, just write down what you think you need, right? So what's here? If a ray leaves this slit, remember the middle normally is a bright fringe. And next to it is dark and so on, right? If a ray leaves here, travels that distance and leaves here and travel that distance, did it travel? Did the distance the same for the center? Is the distance the same? Yes. Right? The distance is the same for the center. What we call that difference, we call that difference the difference of path difference. And what you would recognize is if the path difference is 0, we are at a bright fringe. All right? And there is something else that you'll notice. Next to bright is what? Dark. And then after bright, you will get next bright again, right? And you will get next bright again. I wait on Seville. And I believe Seville coming to class. Oh no, you should on this side there, you're talking Seville. You're on that side. Right. So what you say, Dante? What you say? If a ray leaves here, right? And the ray travels to this next bright fringe. And the next one from here meets there. Who travel longer? Bottom, right? So if you were to draw a line here, this particular distance here is the difference. What you're going to recognize is if you work out that, that's a whole number of wavelengths. So let's pretend lambda is 0.2. That distance will be 0.2. So you would recognize that to get to that bright fringe, the first bright fringe, the path difference is lambda. Okay with that? And then the pattern will follow after that. Second bright fringe, path difference is 2 lambda. Third bright fringe, 3 lambda, and so on and so on. Right? You okay with that? So the difference in path is always going to be a whole number of wavelengths. If it's right. Everybody okay with that? But what would happen? I don't want to color earlier. What would happen if right? We said that dark in the middle here, right? What would happen if the ray travels here and here? Right? It travels into dark, right? Of course, one longer than the next. How much you think this will be? Because remember, just think about this. Bright was a path difference of 0. Here, path difference of lambda. Half of lambda. So if you were to work it out, you're going to get lambda. So if you find the path difference, and you are getting things like this, lambda and 2, 3 lambda and 2, 5 lambda and 2, and so on, it means that you are at a dark fringe. Everybody okay with that? So whenever the path difference is a whole number of wavelengths, you're going to get lambda. I mean, you're going to get bright. When the path difference is in between half number of wavelengths, you get dark. Anybody could Anybody could relate this to something else that we learned in the parrot? When does constructive interference occur? When the waves are in what? C. Oh, that's not the word I want to hear. When it is in what? Something. Phase. Right? When the waves in phase, what's the phase difference? What's the phase difference between these two waves? 0 and what else? None. Besides that, it could also be in phase. Watch this here. If I give you a wave, but the wave starts, when you hear the wave starts right here. What's the phase difference between these two waves? No, this will be 0. This will be 0. Phase difference here is 1 what? What's the formula? Phase difference. Right? If you watch back the formula, the phase difference is 2 pi. 2 pi is the phase difference. That's okay? So a bright fringe will occur at 0, phase difference at 0, a phase difference at 2 pi, a phase difference of what? 4 pi and so on. 0 corresponds here, 2 pi corresponds here, 4 pi corresponds to 2 pi. That's okay? Joseph, that will occur when the waves are what? Out of phase, right? And when a crest meets a trough, that's out of phase, right? What's the phase difference there? What's the phase difference? When a crest meets a trough, it will be half of that pi. Okay? So destructive or dark will occur at pi, then occur at 3 pi, and so on and so on. Everybody okay with that? So these things kind of line up and tell us when we get in a bright and a dark fringe. Right? All these show in phase, all these show out of phase. Right? Yeah? Am I there? Okay? Let's go on to that proof now. All right, so let's make a note of this. When the path difference is a whole number of wavelengths, we get a bright fringe. When the path difference is at a half number of wavelengths, we get a dark fringe. Negative. A little bit bigger. Right? What's here so you understand what's going on, right? I don't want that. Hard. Guilty material. Right. They can bring it out to be calculated. Right? I want to understand what you're doing. I am doing the proof at the first bright fringe. Okay, to make it simple, right? Right? I'm looking at the path difference from here. The path difference from B to that point, and then this to that point. I call in here O. and I call in here P. Right? You all remember how I showed the difference in part? What I did? How I could show you difference in part here in this diagram. Remember I drew a line down here? 90 degrees. Let's call that N. That's okay? So this distance here is the difference in parts. Here equals to here. That's okay? The only thing I'm adding in for you again, I'm adding in here as theta. And I'm adding in a line from this point. Let's call that OPM. Let's call it M. And I join a line from here to here. And I call in this theta as well. So see diagram? I draw two rays leaving A and B, meeting at P. And then I draw a perpendicular line down to EP to give me the difference in part here. Are you okay with that? And I have two triangles I'm going to focus on. I am going to focus on triangle ABN, and I'm going to focus on triangle PMO. So if you have to do the proof, all I want you to remember, draw these two rays, draw this line to get the part difference, and draw this line. That's it. All right, and then we're going to do the proof together. Hurry up, catch the diagram fast, and we're going to do this proof together. Yes. Huh? We got the proof together. Unless you want to prove it, you can prove it one time. Oh, by the way, I forgot something. Here to here is E. Here to here is the separation of the slits. And here to here is D. Right, just adding that, and we're gonna work out something together, right? That's it, answer zero. Go outside, by class with C. Yeah, those are theta. Right? You might be able to see it, but this system here, but this distance is real big and this distance is real small. Right? So it makes these angles to see. Right? But can I have the show on the plan? I didn't want to predict the difference, but okay, you will have the numbers. You get to that. Yes, like how many lows? No, let's call them theta. Let's call them theta. We're now going to apply laws to it. Right? I just wait on severe to finish that. Engineering, but the same Alright, ready? No, I think you had enough time downstairs already.
就是你是上面从收到什么网从是啊，你要是个是要是有要是，是个关系个是要，我知道就 bro， 是不是不是？
All right, watch here.
Yeah, 三个要做。
All right, so watch here, Ollie. So we need to be able to work these things out. Before we do it, what we said about Bn again? We said Bn is the part difference, right? We said Bn is the part difference. And since the rays meet at the first bright fringe, what's the part difference, Adrian? 1, 0. 1 what? No, not just one lambda. Right? 1 lambda, right? Remember, if it's a whole, if it's a bright fringe, it's a whole number of wavelengths, right? Here's 0, here's lambda, then 2 lambda, and 3 lambda, and so on, right? Some people do the proof, they go to the n and n minus 1, and then whatever do all that, right? We just go into the first bright fringe. So Pn is the first bright fringe, which is lambda. Everybody okay with that? Let's go to triangle. Let's deal with triangle PMO first. Let's look at triangle PM. Something wrong with letters today, but I'll struggle in, right? Triangle PMO. So let's take a look at sine. I'm tan. Tan is what? Tan theta is opposite over adjacent, right? So let's take a look at tan theta opposite over adjacent. So it means that tan theta is opposite is y, right? And this distance is
D.
D. You see now? So it's y on D. Tan theta is y on D. Right? Next thing, triangle ABN. Let's look at this triangle now. Can we find sine theta? Sine theta is what? Sine theta is opposite over hypotenuse. So it's BN over AB. BN is lambda over A. Lambda over A. Right? And here's something that we cannot do in pure math that you have to kind of accept here. That since this distance really big compared to this distance. So since D is much, much bigger than A, it makes tan theta approximately equal to sine theta. Right? The reason for that is if I were to pull this real far away, Tisha, if I were to pull this real far away, what do you think theta would technically become? Well, almost 0, right? And you all remember from pure maths, the limit as theta approaches 0 of sine theta on theta. And that's technically 1, right? And tan is what? Same thing. So it means that as theta approaches 0, sine and tan appear to behave the same, right? So it means that tan is approximately equal to sine. So tan theta is y on D. Sine theta is lambda on E. Move D there. So I'll get y as d lambda on. That's it. All right. So now we're going to learn to apply that. Right? Right? Sometimes they're lucky and they give you a diagram to work with, other times you have conflict, right? So just remember, once you have your diagram, you need these two triangles. Those are the two most important triangles, right? This line are looking important, but this line helps you show that the part difference is this value here. Yeah. For the first,
You can use that to prove the same.
you can do the same principle.
Please.
Sorry.
Please.
No. Because if you put it in the middle here, what would the distance here be? Half point. And here will be lambda on 2. On a simplified, here get simple. Same principle, could root. But really and truly, a more formal proof is not full, is n and n minus 1. So you do the same thing for the n fringe, your n lambda, n minus 1 will be n minus 1 lambda, and yeah. Right? If you look at it, know something that you want to did as well.
So much fun.
And this will be 20 become 5, 6.
Happens.
Intersect and 20.
So the graph is like 4 months.
Huh?
A graph is like
Yeah, graph is like 4. The plot a graph and what. Alright. Let's apply this now, no? I use my MacBook. Copy that up.
你现在会议这些，那全部，那全部去。也来这个，也。多一点。
Right, let's try one. Right, so if we remember, can I apply this to like sound and thing as well? Right? If I apply this to sound, then instead of a bright, what you will get? Loud. And then you have soft in between and loud, right? So you have all these different questions here. Real life or was it one? We want to know one. No, Try this, please. That's that simple here. Do I really prove? Do I really prove because on board, right? Right, don't worry. Part one, they ask you to prove, right? Right, started part 2. No city Gilbert. From phone and go question but now. Train open us.
So yeah, people who.
It's for us.
Everyone shot you. I see. Oh, it's a blood.
Was he on Kiara?
Kiara. Well, it's only inflation.
Real work. Mikhail, I say this good, but I'm trying to works. message my answer.
Same question.
No, I say ignore the proof. You don't be listening, boy. Part two, it doesn't part two alone. Yeah, let's kill off that. Ethan, you didn't come and ask after. Or I guess you did me. Yeah.
I thought you were talking about every part of it to be like.
Well, them already. I want to finish up that this weekend.
I was it's a I don't think the education I'm draft. Making model.
Don't worry, we clean it all. After the event, that's what. So, all right. Now done. Right, just figure out what is Y and what is D and please work in the correct units, right?
Jack out.
You was online?
Yeah.
It was online.
Yeah.
That's not that he can.
Yeah. One other ready.
Tell us figure these.
Oh yeah.
So the lady had opened her card, that's started to give it forward.
See, because Adrian again, everybody is thinking split. You see, I shut them onto them. It's nice single. Very sad.
Alright, time up. Let's do it again. Right, so all you really had to do there was just figure out what is Y. So the Y is displacement, so we have Y here. And distance from the screen is D. Fringe. Oh wait, no, sorry, let me stop.
Why?
That's it. Sorry. And the fringes are Y apart. And they want us to find lambda in nanometers. So rearranging the formula, we rearranging this formula and we'll get lambda is YA all over T. Y is 1.4 by 10 to the minus 3. Yeah. 0.2 by 10 to the minus 3. And D is 0.5. Right? And what you all got for lambda there?
5.6.
5.6 by 10 to the minus 8. But they want the answer in nanometers. Nano is minus what? Nano is minus what? Minus 9, right? Minus 9. So what to do? What would the answer be in nanometers? Why is it looking so weird? Are you sure it's 5.6? 5 to the minus 7, right? Let's check back and see. Yeah, minus 7. Right? Because remember the colors, right? So that's 560 nanometers. You want the answer in nano, right? So yeah, move it decimal place, press decimal place 2 times. Nano is 10 to the minus 9. Well done. Next one. Which have we got to that? Sure. Let's try this one here. We'll make it a little smaller. Hold on. We have one more afterwards, right? So below we have a little setup. Right below we have a little setup as a microphone is moved along XY. You're seeing that? So you're moving a microphone along XY. It detects a maximum of sound at O and then at X. So here's a max and here's a max. Everybody okay with that? So it's starting from Y and it's going down, right? So anybody can guess what Y probably is? A minimum, right? And Joseph, a minimum. Right? We don't really need diagram. Actually, need diagram. Sketch a diagram and let's work out this now. You don't need the info on top, right? Just remember that X is a max. X is a maximum, right? Just sign up, right? Yeah, but everything that you do already has nothing to do with it. They do your master. They get master. No, not scholarship. Give example of it or the master. I can write to try and take this master. When I sign up. When I sign up, it's good. No, because that's what the matter player, right? Let's find out. Not because we don't lose things out. Oh, you don't lose that in. But it's good up there. Some of them boys do that last thing. To the way to find px and they want you to find qx. Any ideas? And hence finding wavelength. So everybody pick that up, that's what I have, right? How we doing that? Joshua, yeah, so Joshua, any ideas? Copy what? Yeah, just the length of a line is what? Not sine, but you can probably use Pythagoras.
Yeah.
Try Pythagoras, come see. Anything number feel boring? Huh? Huh? First, calculated. I don't think so. But last year was a class. Yeah, the exam, the next one.
So we have a class to do, right?
Yeah, that's why.
And your,
So you just tell them, right?
yes, tell you, so we have to tell.
But you will tell the office, so they will say, but all the classes,
There's people, 19 people.
right? So what they will do is they will like stay there. And which one first?
And it's the same time.
How many now? You want to know you can.
In one.
So they might like stay there, one at a. That's the same example, no, they had it. Not really, so let me go with my people. So they got a 10, great, but sit up, what's your other people? Well, because it yeah, because she'll make it work.
But you don't make two of them.
The last time she does give order. I don't know. Because you need to, because we did there one time. And they would just take it and go.
If we are here.
Oh, do the same class.
See, can you click on the sentence?
I guess, I think you can ask to that over. Alright, let's see what you got now. So we're using Pythagoras. What's the distance here? O to y is what?
Yeah, so it's like.
0.75, very good. right? Because remember it's just in the
That's your bad.
kind of, yeah,
Oh, okay.
it's just in the middle here. So that's 0.75. So Pythagoras theorem, I got px to be the square root of 6 squared plus 3.25 squared. How much is that?
6.82.
6.82. And then you want to find qx, which is the square root of 6 squared plus 1.75. Yeah, 1.75. Is it?
0.75. Oh, yeah.
And I have to minus
Yeah.
this
yeah,
off.
fine. Oh,
How much you got?
6.5.
6.25. So the part difference is how much? Well, I got 6.25. Everybody get that? 6.25. So the part difference is equal to 6.82 minus 6.25.
Oh,
That's the part difference, right? But why I need that?
Fine.
To find lambda. Right? So Nathan, since it's the first right fringe, sorry, since x is the first maximum, what's the part difference at x? X is the first maximum. What is the part difference?
One.
Look at the same thing again. So one what?
One.
One lambda. Right?
It's one.
One lambda, right? So the part difference is 6.82 minus 6.25, which is
0.57.
0.57.
Yeah.
That is your wavelength. But notice we did this without the formula, right? Have you recognize that? Now do it with the formula. See where you get. Find for lambda with the formula. Right? Adrian said if we do get the same thing.
Ask them now.
Yeah, they explain why.
One.
Do you want to explain why?
I say I never. One step I forget.
I see. So have to explain why. Right and see. No, nothing more. Use the formula in part 2 and tell me what you get for y. For lambda, sorry. So y is what? But y to be what? 0 point, that's y? For sure. And y is the separation between maximums, right?
Oh,
So at the maximum will be at O and a maximum at X. So 2.5. A is what? 1.5. And then G is what?
6.
Simple.
0.2.
How much here? 0 point what?
6. 6.
625?
Yeah. Now, I can.
625? Oh no, I thought the answer was so. Right. But why the answer so the different there, Mikhail? Okay, you just check what ChatGPT say now. Yeah, let me hear. That's how you jump on it. Why are the answers different? Alright, so number one, which one? Small angle. Right, so because, so which one is more accurate? Part one or part two? Two? But remember, in part two, we use this formula here. And we had to make an assumption. So because of the assumption, right? Because of the assumption, it means that this is a kind of approximation. So which one will be more accurate? Part one. So the values here. So the values are different because in part two, the formula that we derived is an approximated formula, right? Because of the approximations here, right? So you have to tell them this. The reason the answers are different is because in deriving the formula, we approximate that D is much bigger than. That's okay? We approximate this here. Right? They have that after. Discuss the facts. Right? Discuss the fact that the values in B1 and B2 are different. Huh?
Okay.
Yeah, that's how we now explain it. The values are different because in deriving the formula, we made an assumption that T is much bigger than. Right? Find out? Yeah, catch it together. Can you check it? What's that? Is it? Oh, okay. I thought you used it. Right, and then find frequency. Or you find any frequency. Yeah, speed of sound is what they gave us to use. They told us, well, use the speed of sound at 330. So find F now. What's the formula we're gonna use here? Dante? What's the formula we use in this part there? Define frequency? Yeah, define frequency. Huh? What we getting now? Huh? Right, so V is equal to F lambda. Lambda, sorry. Sorry, yeah, V is equal to V on lambda. Right, and it's sound, right? So speed of sound, we could use like 330. Question, which lambda value would you use? Which one? It's like a more accurate one, right? 0.1? 57. 330 over 0.57. Huh? That'll be in hertz here. How much is that? $578.9, right? Right, last question. Let us go to Joseph. Joseph, last question is for you. Sorry, last part, but we have one more to do. Joseph, how are you doing that? The phase of this speaker is changed to 180. What effect will this have on this sound heard at O and X? The phase change to 180. So initially the in phase, right? Crescent and crest meeting giving you a loud sound. Now the outer phase, crescent meets a what? And what you will have happening? Destructive. So you will get a what? A minimum now, right? You will get like a minimum now. So at O and X, you'll end up with minimum. Are you okay with that? Last question. Write it down now, please. I like something that's one. Right, last one. I just like you are comfortable. Have a class for that. Same thing that we do it. Same thing that we do it. Oh yeah, last one, and then we can introduce the fraction weighted. This last question now, please. Last question. I don't know if go back to it. Where was it? One of them.
9 months.
USA. What is it? Let's set it up blank page.
Yeah. Collection. Because it is. I want to touch.
Hey, the group by confidential. Well, you could also use, you could also use, actually, I think it probably comes out similar, something like this type. Huh? You could also have that. You could also use this. But of this, did it pull back into, right? Now, the next one, when it doesn't sort of. No, they're parallel, they're parallel. First sheet, that will be good. No, this general. But what happened if it's parallel? It's zero, right? But it's gonna be first sheet is zero. But you will reach a point where you recognize that it's similar. Well, and it's not all. So it's similar projected root as well. I like this, We take some. Well, what happened now is that sometimes I like where we have to go to it. Might just be wrong. If you feel like we see like one of people. That's so you guys are something that stick to system of so like for solutions are not bad, like especially those who like watching the solution. Somebody else send somebody is helping somebody on the website. When you see it looking like somewhere, somebody else. Well, I just start seeing the mark for the solution. Yeah, I'm finished, right? But yeah, but pictures testing.
Good, 变小声一个对。
Huh?
变小声。
Kesha, there you go now. Right, so we have a loudspeaker separated by 0.5. So that 0.5 is what letter, Kesha? Why? What is that? Nothing more. Think about it, actually. Separation between the slits. So that's A, right? So 0.5 is A. The speakers are connected to an output of an amplifier and they form sound wave with an amplitude at a frequency of so much. So they give you the frequency, right? And they give you the speed. So what you can find there, if you have frequency and speed. If you have B and F, what you can find? Lambda, right? So you can find lambda. And then the amplitude emits two waves 180 out of phase. What does that mean now? 180 out of phase. What we got here in the middle? Nothing. So you're going to get in the middle, you're going to get so. Next to that, you will get maximum, and next to that, you will get soft again, right? And the semicircle has a radius of 30 meters. Well, what does that 30 meters represent? So we said here is 0.5. And we said we could find lambda by doing this. What does that 30 meter represent? The separation between the source and the source and the screen for the observing point, right? Next. Calculate the amplitude of the wave at the chair on the perpendicular on the center line. What will the amplitude be here? Think about it, y'all. It's real simple. Don't overthink it. Who says 0? Why is it 0? So you have to flip it back to it first. Why? Why is the amplitude zero? He correct. He will from ChatGPT, so it's correct. But why?
We have 40
And like husband, why? You just said why. Are they in phase or out of phase? Out of phase. So what you will hear, the central point. Nothing. And what's the amplitude of nothing? No, some. Zero. Right? Zero. So it will be dark, right? So it will be zero. It will be soft, right? Which is zero. So calculate the amplitude. The amplitude is zero. And the what was the reason why? Right? Because the waves are coming out of phase. Yeah? Yeah. Once all this mess on group. But it's only group so everybody can see it, so they come together. That's better for me. So it'll come in the video also. Right? No, not true. They don't listen, but no, on their way. I get you, boy. We have to question. If you use the wrong custom paper, you are. I think for Chapati book, I think I do that pretty well. If you put the wrong identity, you'll get it. Yeah, but okay with that?
Yes,
Right, do the next part now. The next part, why is not doing it? At what minimum distance d to the right is their maximum? Try to work it out. When will you hear maximum? Work it out, please, everybody. All right, last question. Yes, we'll go ahead and leave your almost done. Why is what? Why is the separation between two similar fringes, right? Bright and bright. Or loud and loud, or soft and soft. That's in the middle. Just in the middle. Right, so what's the formula we using here? We using what? We using y is equal to d lambda on A. Right? We're interested in finding y. We know that d is 30. We know that cos lambda earlier. So it was 330 over what?
44. 0.0. That's 0.07.
Wait, 330 over what?
4400.
4400. And I got how much?
0.00.
Go fast now.
Oh.
330 over 440 was what?
0.075.
0.075.
0075.
0.075.
0.0. Wait, that's not it. One shot, it's okay, yeah, my bad.
Right, 0.075 all over A.
I don't know.
Make up all the mind, yeah?
Yeah, 0.
0.
0.07.
Alright. So y is how much?
Like, oh my god.
4.5?
Yeah.
30 by 0.075 over 0.0. What's that? 4.5. Right? Y is equal to 4.5 meters. So therefore, D will be half of that. Right? Because remember, what you just found out was 2D technically. The distance between a minimum and a minimum. But they want the distance to the right of the central, that'll give you maximum. Right? 4.5 divided by 2 is 2.25. Are you okay with that? Yeah? Alright. Before you wrap up, I just want to show you one thing that we're doing next week, right? Wireless in your head. What we're doing next week is something called diffraction rated. What you get, it's very similar. Hopefully it might stay in your head. Watch this. Let's say you have a slit, right? But instead of 2 slits, you have a whole set of slits. When the light comes in here, it's going to produce a pattern. Right? At the n equal to 0, that'll be a brighter strip. And then you're going to have other strips. N is 1, and it's 2, very similar to what we just did. No. The end is representing where you're observing the diffraction rate pattern. And you're going to get a pattern that looks something like this. So what we're going to look at now is a piece of glass with all these little slits in it. All these slits. And when the light passes through, it produces a pattern for a diffraction rating. Alright? And the reason I wanted to show you this is that there's a formula very similar to what we just did that looks like this. This is the diffraction grating formula. This is the interference pattern formula. So once you see diffraction grating, we come in here now. Once you see an interference, we use in here. Right? And then we'll finish up with lenses and the dots. We've done the